This is a short course on problem-solving strategies, and I'm going to illustrate it with some interesting problems. The problems are not necessarily difficult, but they have counterintuitive solutions. Here's one that has appeared on the internet and has sparked off all sorts of controversy. Here's the situation. You're at some sort of quiz show, and the presenter there shows you three boxes, and he tells you the prize in one of the boxes. The other two are empty. And you then are allowed to choose a box. So you choose one, and without any loss of generality, let's then say that you've chosen box one. Then the presenter opens one of the other boxes. He knows where the prize is, and he then chooses another box, say it's box two, to open, and he reveals to you that that box is now empty. Suppose then this is box two. So this is the situation. You've got three boxes. You've chosen box one. The presenter has revealed that box two is empty. You don't know what's in box three. You are now given the choice. Either stick to your original choice or switch to the remaining box. So what do you do? Do you switch or stay? And on the face of it, you think, well, you're still just looking at two boxes. You don't know what was in the first. You don't know what's in the third. So you'd think, well, it's even chances, 50% chance either way. Now, the objective of this problem is to propose a strategy, the strategy of either sticking with your original choice or switching always to the remaining box, and prove that your strategy optimizes your probability of winning. Here are some things to consider when tackling a problem, especially a mathematical problem. Firstly, of course, you must understand the problem. Now, that sounds a bit trite, but I have seen students trying to prove that a function is continuous, and when asked about it, they didn't fully understand the definition of continuity. So if you're trying to show that an object has got a certain property, you must understand exactly what that property is. In many problems, it's wise to introduce variables and then translate the problem from English into mathematics. So you describe the problem in terms of the symbols and decide which are the unknowns and solve for those. It often helps to draw a sketch. Just anything which will let your mind focus on the problem. Then you can, within the sketch, if appropriate, label some of the things there as variables and then describe the problem in terms of equations or differential equations or something like that. It's very important to make sure that you collect all of the given information, and with especially well constructed tricky problems, information will be there, but it's not obvious. It will be revealed in some subtle way, and you need to make sure that you've got all of the information. If the problem is well posed, you will not be able to solve it unless you have all of the information. Then you describe the problem in terms of the variables, and from that, usually you'll make equations or differential equations or something like that. Be absolutely clear to identify exactly what the goal is. If you're trying to optimize something, be absolutely clear about what it is. So determine the goal first and then use the given information to move towards the goal. You may need to look up or find or develop your own theory in order to breach the gap between what you've the given information and the required goal. And you need to formulate a plan. That is, identify exactly what this problem is about, and then find the appropriate theory, get all of the information, and then use that theory to go for your goal. So schematically, you identify the goal. You make sure you've got all of the given information. Develop or find or recall the appropriate theory, which is going to lead you from the given information to the goal. Just for some extra tricks and hints, if you've got a fairly complex problem, very often you can pose a simpler problem, which is similar to that one, and see if you can solve the simpler one and then generalize to the one that you're considering. When you have solved, don't leave it at that. Have a look at the solution. Make sure that it makes sense. And then from there on, see if the problem can be generalized. So if you say solving a problem to do with something in 2 dimensions, can it be lifted up to 3 dimensions and higher? Then when you finally solve the problem, you've been writing down your thoughts and calculations on a piece of paper, then write it up properly. So that if this is to a problem that you're solving in an exam, then you, or further down the line, if this is some problem that a research problem, and now you're going to write it up, you've done your calculations on the side, on pieces of paper or on the computer. Now you write it up so that it is presented so that one of your peers can understand it. So if you're a student at school or university, you write it up as if you were explaining to one of your peers. If you are doing research, of course, you then write it up for mathematical professionals. So back to our problem. Remember what it was. You're given 3 boxes. You've chosen, say, box 1. The presenter reveals that box 2 is empty and then invites you. Would you like to switch to the remaining box, box 3, or stick with your choice? Now, in order to get a fix on this problem, what is it that we're trying to achieve here? We're trying to optimize the probability of picking the box with the prize. That is it. It's the probability that the box that you have has the prize. What are we given exactly? You've got to extract all of the information out of this problem. It's tempting to say, well, now one of the boxes is empty, so this is equivalent to just looking at 2 boxes and choosing one of them. So it's tempting to think that there's an equal chance, regardless of whether you stay with your original choice or switch to box 3. So you know that box 2 is empty, so faulty reasoning would lead you to think that it doesn't matter. This is wrong. There's more information. So here is our situation again. There are the 3 boxes, and you've chosen box 1 randomly, and the presenter has revealed box 2 to be empty, and he knew this. Now, I know it's subtle, but that's information that has been injected into this problem, this information that this presenter knew that box 2 was empty. So just to formalize this, let's let Pi be the probability that the prize is in box I. So before the presenter gives you this choice, P1 and P2 and P3 are all a third. The prize is equally likely to be in any of the boxes. So here we are again, box 1, box 2, and box 3. Pi is a probability that the prize is in box I. So the probability that the prize is in box 2 or box 3 is the sum of the two probabilities. These are disjoint events. So the probability that it's in box 1, which you chose, is 1/3. Probability that it's in box 2 or box 3 is 2/3. Probability that the prize is here is 2/3. But now box 2 is empty. So the probability that box 2 contains the prize is 0. P2 is 0. And that means P3 must be 2/3. And that then means that you should switch. If you remain with your original choice, probability of getting a prize is 1/3. If you switch to box 3, the probability is 2/3. So there's your strategy. The switching strategy will give you a probability of 2/3 of getting the prize. Now let's take a different approach. There are two cases. The one strategy is to stay with your original choice. There are 3 boxes, and the probability of the prize being in any one of the boxes is 1/3. So if you stay with your original choice, the probability of winning is 1/3. Now what if we adopt the strategy of always switching to the remaining box? Say, for example, we chose box 1, box 2 is revealed to be empty, and so we switch to box 3. If initially you chose the correct box, then when you switch to the empty box, so you lose. And that's the only way of losing. There are just 2 choices. You either stick with your original box, or you switch to the remaining box. If the original one had the prize, the one you switch to doesn't have the prize. So that was the situation, and that is the only way to lose. So the probability of losing is 1/3, and the probability of winning is then 2/3. Just on the other hand, suppose you initially chose incorrectly. In other words, you chose an empty box. When you switch to the only remaining box, which must have the prize, because the second one is empty. And if you chose incorrectly, then the first one is empty and the third one has the prize. And what's the probability of initially choosing an empty box? That's 2/3. So the probability of winning is 2/3. This problem is sometimes called the Monty Hall problem, and sometimes it's the goat problem, because it was initially posed by saying there's a prize in the one and a goat in the other. Now look, I come from South Africa, and goats are quite highly prized here, so I don't think that's quite appropriate. So let's stick with the Monty Hall problem. And if you still have doubts about this, just try this out. All you need is a small number of experiments. So you get someone to act as the compere or the presenter, and you do this 24 times. And you adopt the strategy of switching every time. So you get him to put the prize in a box, then you pick. He must reveal an empty box, and then you always switch to the remaining box. You'll find that if you do this experiment 24 times, you're going to win about 16 of those 24 times, roughly. If you're still doubtful and you don't want to actually do a physical experiment, let's write a MATLAB script or in any other language. It's a very, very simple program. This is just housekeeping. It describes a situation. We're going to get input from the user, the number of trials to run, and then we will make a 1 by n vector, which is going to be the vector which records the cumulative reward that we get by adopting the switching strategy. We'll make a loop to simulate this process. Remember, there were going to be n experiments. We'll make a vector x with all zeros in it. Those are the boxes. So initially the boxes are all empty. Now we're going to put a prize in one of them, and we're going to guess one of them. So we use the MATLAB random number generator, which generates integers. The 3 here, it generates integers from the numbers 1 to 3, and it's a 1 by 2 matrix. So here's an example, 3, 1. And we'll take the first of these, call that little p, the first in capital P, and that's where the prize is going to be. That's the prize position. So our vector x now, x at position P, is a 1. So this list of boxes here has a 1 in box 3 and 0 in boxes 2 and 1. The guess position is the second element in capital P. Yeah, this one, 1. So the guess position is 1. So the situation in this particular instance is that the prize is in box 3 and 2 of them are empty, and you've chosen an empty one. Then the empty box positions we can get from where the prize is. So the prize is in position 3. So we take the set difference between those numbers 1, 2, and 3 and P. Of course, that then is a vector with the empty boxes in it. Then the compare, the presenter is going to indicate a box Q which is empty. So he chooses the difference between the B, the 1 and 2, and your guess position, which in this case was 1. So he reveals that box 2 is empty. If there were 2 empty box positions, then we'll just pick out one of them, and he's got to reveal to you an empty box position. Then we're adopting the switching strategy. So your new guess position is obtained from the set difference. And then we will keep a record of the reward. So on your new guess, I'm calling this a new guess reward, it's x at new guess position. And we make a vector called reward, whose kth element is this. Then we'll end our loop. Then we will form the cumulative sum of those reward vectors, and then we'll compute the percentage of our percentage which we've won. And we'll send this information to the screen, and then we will plot. This is just a little, we want to plot the cumulative reward. This is what it will look like. So these are the experiments, the trials, if you call it that. In this particular instance, I've run it 100 times, and this is how the cumulative reward has gone. So out of 100, around about 70 you've won. And if we do it, say, 10,000 times, then there it is, around about 6,700 and something, your cumulative reward. You've won about 67% of the games. Now that we've solved this problem, and you should do this with any mathematical problem, take a look at your solution and then see if you can generalize the problem. Here, the problem involved 3 boxes, so a natural extension of this problem is, what if there were 4 boxes? So then, there are 4 boxes, the presenter gives you a choice, you pick a box, he then reveals a different box to be empty. You can then choose one of the remaining 2 boxes in this case. What do? Do you switch? What is the probability of winning if you always switch when there are 4 boxes? And now, if you've handled that, What if there were n boxes? Pause the video here and see if you can solve these two extended problems which extend the previous one. Pause it here, see what you can do. Only go forwards when you've had a good shot at this problem. Now let's extend this problem. Instead of there being 3 boxes, suppose we've got 4 boxes, and the prize is in one of the boxes. And you choose a box, so you say you choose box 1, and the second one is revealed to be empty. Then you are allowed to switch to one of the remaining 2 boxes. Of course, if you remain with your original choice, the probability of winning is a quarter. If you switch to one of the remaining boxes, then the probability of the prize being in box 2, 3, or 4, one of the 3 remaining boxes, is 3/4. But this one is empty. Box 2, say, is empty. Probability of the prize being in there is 0. The sum of the probabilities is 3/4. So the sum of these 2 probabilities is 3/4. The probability of the prize being in either one of them is a half of that, 3/8. Well, we've seen what happens in the case where there were 3 boxes, and then we've extended it to the case that there are 4 boxes. What about n boxes in general? Just let's set the stage and let Pi be the probability that the prize is in box I. So initially, there are n boxes, and the probability that the prize is in any of those boxes is 1/n. Now, with our previous setup and without any loss of generality, suppose then we choose box 1, the presenter reveals that box 2 is empty, and we're going to switch to box 3. The probability that the prize is in box 2 or box 3 or box 4 up to box n is the sum of those probabilities, and there's n minus one of them. So the probability that it's in box 2 up to box n is n minus 1/n. But after he's shown that the box 2 is empty, the probability P2 that it's in box 2 is 0. So in this sum over here, P2 is 0, and this remains the same. So the sum from P3 up to Pn is n minus 1/n. And they're equiprobable. They all have the same probability of occurring, and there's n minus 2 of these. So the probability that is in box 3, or any of these, is that divided by the number that we have here, which is n minus 2. So the probability, for example, that it's in box 3 is this divided by n minus 2, which is n minus 1 over n into n minus 2. And we can just rewrite that as a factor, n minus 1 over n minus 2 times 1/n. That's the probability of it being in the first box. That's the probability of winning if you stay with your original choice. Also note then, if we make n equal to 3, then we get back our original probability. Here, there'd be 3 boxes, and the probability that it's in that third box is 2/3, that we discovered before. Let's just rewrite this a little bit differently. Let's make these definitions. P stay is the probability of winning with the stay strategy. P switch, the probability of winning with the switching strategy. And that factor, Fn, n minus 1 over n minus 2. This is always greater than 1. Note that. You can't put it, n's got to start at 3, and when we start at 3, this factor is 2. It's always greater than 1. So let's just rewrite this. Write our n minus 1 as n minus 2 plus 1 and divide now n minus 2 into this. And we see then as n increases, this diminishes to 0 and this factor approaches 1. There's the graph of fn versus n. It starts here at 2 and approaches 1 as n increases. There's a serious lesson in all of this, that probability changes with the given information. Initially, when there were 3 boxes, choose a box, the probability of winning is 1 over 3, 1/3. Then they compare, the presenter gave some information. He revealed that one of the boxes was empty, and that changes things. That's information coming into the system. If you adopt the switch strategy, then it increases your chances of winning. Remember, the probability of winning with the switch strategy is this factor times the probability of winning with the stay factor. And this factor, initially, when n was 3, was 2. It doubles your probability of winning if you adopt this strategy. And this applies to any situation where you're computing probabilities. Say we take the most trivial situation where you're tossing a fair coin, heads or tails. By fair, I mean that the probability of it being heads is a half and tails is exactly a half as well. Toss the coin, guess what it is. Initially, if there's no information there, no other information, your probability of winning by choosing heads is half. But if, for example, you just got to look at the coin and you saw that it was heads, that's information coming into your brain. Now you choose heads, your probability of winning is 1, because the probability of it being tails is 0. Now that's a trivial example, but that is what's going on here. And I'll put up another problem then which uses this idea, and I'll address it in the next video. Now here's a very simple problem to do with probabilities. A man's got 2 children, and he tells you that one of them is a boy. What is the probability, let's call it P, that he has 2 boys? Now there's nothing special about this problem. It's really quite simple, but you should now pause the video and write down your solution. Here is an extension of that previous problem, which you should have solved now. Man has 2 children. One of them is a boy born on a weekend. Now, let's call the probability P that he has 2 boys. What is the probability now? And what is this information about being born on a weekend revealing? What has that got to do with it? It's information coming into the system. And the probability now changes from the previous situation. See if you can work it out. Pause the video and see if you can solve this problem. If you've solved that one, now let's extend this problem. A man has 2 children. One of them is a boy born on a Sunday. What is the probability that he has 2 boys? Now let's extend it a bit further. What if he has 2 children? One of them is a boy. This boy is born on a Sunday morning. So now this information is getting more and more specific. What's the probability that he has 2 boys? Now, here's another one for you to chew on. This is about a rare disease which is in a community, and this disease affects 1 person in 1,000. Now there's a test for this disease, and it's 99% accurate. So you go and have this test, and you test positive. What is the probability that you actually have the disease? Now, again, this is not difficult, just a bit of arithmetic, but this questionnaire was sent to thousands of doctors, and they nearly all got it wrong. So see what you can do with this. The answer is a little counterintuitive. Here's another problem. You've got a volatile mixture, and say you have 500 grams of it, and it's made of two substances, 99% of substance A, 1% of B. And A is volatile. It evaporates. So you have your 500 grams, and you leave it for a bit. And when you test it again, it's now 98% of A. So it was 99% of the volatile substance, and now it's 98%. What does it weigh now?